Linear algebra is everywhere. Behind the graphics on your phone, the recommendations on Netflix, and even how Google Maps finds the fastest route. But most linear algebra courses skip over the why and how behind these real-world applications. In this series of linear algebra videos, we are changing that. Mathematicians often create linear algebra content with a focus on the power and beauty of abstraction. The abstract nature of math is what makes it so powerful and applicable to many different contexts. But this can leave out two key aspects: the process of abstraction, which often comes from patterns across real-world problems, and how these concepts can solve real-world problems. I highly recommend Grant Sanderson's 3 Blue 1 Brown videos on linear algebra. He does an outstanding job with his approach, and we've included a link to them in the description. That said, their series largely focuses on abstract concepts, with only one brief context mentioned in the first video of how house size and cost can be represented as a vector. This has echoes of linear algebra classes I have sat in, where the first day the professor mentions several places where linear algebra is applied, and then never actually uses any realistic context or applied problems for the rest of the semester. But not in this series. Here we aim to teach linear algebra through real-life contexts and applications, in the hope it will add some insight and meaning to the abstract ideas. First, we need to answer this question: why do we need the subject of linear algebra? Because the math you have learned up until linear algebra has one big limitation. You can only use individual values, or what you might think of as one number. The basic operations all take one individual value and combine it with another individual value to get another individual value. That is limiting, because so many contexts call for math that works on packets of numbers. For example, the nutrition facts on the back of a peanut butter jar. There are a lot of numbers there. If you only care about one of them, say calories, then you can use your grade school math. But what if you're interested in your protein, fat, and carb intakes as well? Or other vitamins and minerals? Then we have a problem. We can't just eat the protein from the peanut butter and leave out the fat and the carbs. When we take one serving of peanut butter, we take in all the nutritional elements. If we cut out servings of peanut butter from our diet, we cut out all of those nutritional elements as well. To think of a serving, we have to think about all of those values tied together. If we want to adjust our diet's total fat, protein, and carb intake to hit a certain goal by adjusting the amount of different foods we eat, say lower fat by 20 grams, increase protein by 20 grams, lower carbs by 100 grams, then we need a way to represent the packet of nutritional values for each of the foods and to do math on those packets of numbers. This phenomenon of doing math on packets of numbers comes up in a variety of contexts. Financial engineers deal with funds that come as packets of values, like price and recent growth and 52-week highs and lows and risk measurements. When building a portfolio, they must manage the trade-offs of these combined characteristics, not individual components. Similarly, network analysts use packets of numbers, like lists of ones and zeros, where each entry represents connections or no connection between individuals. Sports rankings also rely on packets, with teams represented by lists indicating wins, losses, and unplayed games against other teams. In all these cases, the key is understanding and working with these packets of numbers to answer questions like, which team is the best? Who's the most influential person on a network? What's the optimal investment portfolio? How do we adjust food intake to reach nutritional goals? To answer these, we need to do math with packets and understand the math of packets. So, on to linear algebra topic number 1. What is a vector and what is a matrix? A packet of numbers is called a vector and is usually written as a list, either horizontally or vertically, with square brackets, although some fields use different notations like this one. But if we can put an individual real number, something we will later call a scalar, into packets, a natural thing to wonder is if we can put packets of numbers into larger packets. Yes, we can. Packets of packets become matrices, two-dimensional arrays. For example, in a networking problem, we can put the packet of ones and zeros for each person into a packet of packets called a network matrix. We could extend even further into packets of packets of packets of packets as far as we would like. Those are called tensors, but the math for an introductory linear algebra course only focuses on matrices, vectors, and scalars. You should already be familiar with the math of scalars, since that's the focus of the math of the first years of school. So the math of vectors and matrices will be our focus. You have seen packets of numbers before. A point on a coordinate system has coordinates that can be thought of as a packet. But you were probably not taught how to add one point to another or multiply one point with another, and what those might even mean. We can better understand operations with packets by using a simple context to help guide the math. Let's use our food example from before with the protein, fat, and carb content of food. But I will use just fat and protein and only eat peanut butter and slices of bread. I looked at the nutritional facts of a serving of peanut butter and found that one serving has about 15 grams of fat and 8 grams of protein. A slice of bread I found had 1.5 grams of fat and 6 grams of protein. We could represent these as a packet or vector for peanut butter and another one for bread. Now, even before we started to talk about packets, if I asked you how many grams of each of these I would eat with a slice of bread and a serving of peanut butter, you would have just added the fat values to get the new fat value and the protein values to get the new protein value. So it makes sense if we add these two packets of fat and protein to add the corresponding values to get a new vector of the total fat and protein. Since this is the way the vector addition makes sense in contexts, then it also makes sense for mathematicians to define vector addition that way for any vectors. Notice that if we had one vector of fat, protein, and carbs, and another with just fat and protein, we don't know how to do the addition. A mathematician would say the operation is not defined. If we label values, we can at least get totals for the fat and protein, but we don't know what to do with the carbs. Does a slice of bread have no carbs? Well, no, bread has carbs, so we can't just add a 0 to that last number. Without labels, we don't even know which value might be the carbs. I could have put the new value anywhere in the list of values, so then we can't even get totals for fat and protein for sure. Because of these issues, we only define vector addition and subtraction with vectors that are the same length, so each value in one matches up with a value in the other. We could represent our peanut butter and bread vectors on a coordinate grid, with the horizontal axis in grams of fat and the vertical grams of protein. We could now plot the points corresponding to a serving of each. But we have a problem. How do we make sense of adding points geometrically? Or should we even try to do it? We're not even sure if a vector can be represented as points. Is it helpful to think of vectors as points? With these 2 points on the grid, where would you expect the sum of these 2 points to be? We could try to plot our total vector as well and see if that helps us. Why would adding these points put the total way out there? It might not seem obvious. Let's go back in time. You may have used arrows to add or subtract numbers in the real number line like this when you were first learning addition and adding integers. We can line up the arrows to measure the distances and visually see the total distance gained or lost. This arrow strategy might help us. We need to line up arrows that go from 0, or the origin, to the points, but the arrows needed to stay in the same direction, in the same way that the arrow representing -5 kept pointing to the left. Sure enough, the last arrow points to the point representing the 2 values we expected. Notice that it doesn't matter which one we move, we end up at the same point. We can use this same reasoning to figure out what subtraction of vectors looks like on a coordinate grid. For example, if we have a peanut butter sandwich made from 2 slices of bread and a serving of peanut butter, we would have a total fat and protein consumption of 1820. But now if we subtract away a slice of bread, we should be back to this point of 16.514. Notice to go from 1820 to 16.514, we move in the opposite direction and distance than the vector 1.5, 6. So a move of a -0.5, -6. Or we can make the whole vector negative vector 1.5, 6. So the resulting vector of 1820 minus 1.5, 6 is 16.5, 14. And that is the vector that moves from the tail of the first vector to the head of the second. One thing that may be bothering you is, why is it okay for us to move the arrows around? If we move a point, it's no longer the same point. Why is it okay to move the arrow representation of the vector? Won't that make it a different vector? Well, in short, no. Vectors are better thought of as changes in position, not the positions themselves. The change from the origin to 15, 8 is the same change as 1.5, 6 to 16.5, 14. This makes vectors more flexible than points. Vectors can refer to a change in position or specific point if we know where the vector starts. If the vector starts at the origin, then we say it is in standard position, and the vector x, y points to the point x, y. Okay, so in this video we saw some contexts where it made sense to think about packets of numbers, which we called vectors. We even learned how to do some addition and subtraction of the packets, and saw what addition and subtraction of vectors looks like on a coordinate grid. In the next video, we will find one way to generalize multiplication to packets, and we'll see how to use it to create your own date match service. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.